My name is Madhudail and my roll number is 241101887.
Hi, I am Madhu. My roll number is 241101888.
In this experiment, we will analyze the magnitude response and phase response of two components, a piezoelectric sensor and a photodiode. We will determine their key characteristics, including the resonant frequencies of the piezoelectric sensor and the 3 dB cutoff frequency of the photodiode.
So this is experiment 1 and we have taken a frequency of 1 kilohertz and amplitude of 5 dB and offset of 5. So we have taken the input from the signal generator to the speaker and it creates some vibrations. We have read it in channel 2 and we have read the input in channel 1. So as you can see, the channel 1 is the yellow one and it is you can see the values fluctuating frequency and VPP, and the blue one is the output. You can see for that too. Thank you.
These are the readings for task 2. V1 is input in millivolt and V2 is output and it is in millivoltage. This is frequency, this is phase and this is gain. So okay, now this is ratio frequency, F higher, F lower, bandwidth, quality, Q factor, and this is graph phase versus frequency, and this is graph frequency versus gain. So the question number 1 is, what are the resonant frequency and Q factor of the piezoelectric sensor? We have found peaks of resonance at 300 Hz, 11,000 Hz and 13,000 Hz. Where the sensor has highest response, the Q factor was determined from the formula Q equal to FR by del F, where FR is resonance frequency and del F is the bandwidth. The higher Q factor means sharper resonance, so the sensor will be more useful in accurate vibration detection and filtering applications. The second question is, what is the 3 dB cutoff frequency of the photodiode? Answer is we established the 3 dB cutoff frequency at Hz, indicating that the photodiode effectively detects light signals of frequency below this value. At cutoff, the output voltage falls to 70.7% of the fall value, which signifies the useful bandwidth. This is significant in areas such as optical communication, where increased photodiode response allows for higher data rates and minimal loss of signal.
This experiment illustrates the effect of frequency response on the performance of the piezoelectric sensor and the photodiode. The knowledge of resonance frequencies, Q factors, and cutoff frequencies assist in the optimization of these devices for practical applications like vibration sensing, structural health monitoring, and optical communication system to provide more accurate signals, quicker response, and greater efficiency in the data transmission and detection. Thank you.
In this experiment, we will explore the behavior of a photodiode when exposed to varying frequencies of light. Using an oscilloscope, we will use an LED as the light source and analyze the voltage response.
Now coming to the procedure part, a signal generator drives the LED with a sinusoidal signal with a DC offset to keep the LED on. The photodiode operates in a reverse bias, producing a current proportional to incident light. When we come to the measurement setup, we connect a 330 ohm resistor to the LED and a 10 kilowatt load resistor to the photodiode as seen in the circuit. Channel 1 of the oscilloscope measures the input waveform across the 330 ohm resistor. Channel 2 captures the output voltage across the 10 kilo ohm load resistor. Thank you.
I am going to explain the connection circuit for task 2. First, I connected the signal generator to the LED light source, and I also connected the oscilloscope to the LED light source, so we could get the input waveform. After, I placed the photodiode in front of the LED light, and I also provided 5 volt DC source using breadboard module. I connected the oscilloscope to the 10 kilo ohm resistor and to get the output waveform. I connected the channel 1 to the input source and channel 2 to the output source. Here is the frequency is 1 kHz. If I change this to 2 kHz, you can see in the oscilloscope peak to peak value of C1 and peak to peak value of C2, and here you can see the phase difference. This is the readings for task 2. Here is the frequency in Hertz, input C1 in voltage, output C2 in millivoltage, phase C1 minus C2, and this is gain. Here is the graphs that I plotted. These graphs between photodiode gain versus frequency, and this graph between photodiode phase versus frequency. This is the resonant frequency, and cutoff frequency is 6 kHz, and this is the code. So now we talk about interface.
The photodiode behaves as a light-dependent current source converting optical power into an electrical signal. As frequency increases, we observe a roll-off in magnitude, suggesting bandwidth limitations. Phase response shifts indicate a delay between the input and output signals.
Now, the question number 1 is, why do we need a DC offset in LED signal?
LEDs need a minimum voltage to be able to conduct and light up. The DC offset makes the LED stay on during the entire experiment and never turn off when it's on a negative cycle of the sinusoidal signal, so the light is emitted continuously. Second question was, why is the photodiode is in reverse bias? The photodiode is in reverse bias for a greater sensitivity and better response time. This is done by broadening the depletion region, decreasing junction capacitance, and lowering dark current so that the photodiode responds more quickly and precisely to light. The last question was, how do resistor values affect the circuit? Greater resistance to load raises output voltage but can be noisy and cause a delay in a response. Reducing resistance enhances speed and response time but decreases the output voltage, rendering weak signals more difficult to pick up. In conclusion, we were able to study the photodiode's reaction to different frequencies and prove its capability as a good light sensor. The experiments show that performance is determined by important factors like circuit parameters, load resistance, and frequency response, which affect sensitivity, response time, and overall efficiency in detecting and processing optical signals. Thank you.